In this video, we're going to do example 5.5.3, where we're asked to show that the integral from minus infinity to infinity of e to the, oops, there's a minus sign missing, e to the minus 1/2 x squared dx is root 2 pi. So why do we want to look at this integral first of all? Well, this curve, e to the minus 1/2 x squared, is a bell curve. And so that kind of bell curve is super useful in probability and statistics. It's what the normal distribution is based on. And to have the area underneath this curve represent probability, you need it to be a total area of 1. And so we need to find the area under this curve and divide by it, in other words, to normalize it to turn the area into 1 for the PDF of the normal distribution. So that's issue number 1. Issue number 2 is, but wait, this is a single integral, and we're doing double integrals in polar coordinates to boot. There are no polar coordinates there. And it turns out that there's a lovely little trick to evaluate this using polar coordinates. Why don't we just evaluate it straight up, you ask? Well, this is one of those functions that does not have a simple antiderivative. It's not possible in terms of elementary functions to write down the antiderivative of this, so getting this number as a single integral is actually very difficult indeed. So what we're going to do is write our integral, and we'll call it I, and we'll say this is the integral that is given there. And then our little trick is going to be to square it. So I squared is going to be that integral multiplied by itself. And then we'll have to remember at the end to take the square root of the answer that we get. Now this is just a number, right? That's just a number, the area under that curve. And so if I square it, I multiply it by itself, I can write it in terms of whatever variable I choose. It's a dummy variable anyway. This is just a number. But the usefulness of doing that, writing this in terms of x in first integral and in terms of y, is that we have seen a lovely theorem over a rectangle. Now this isn't quite a rectangle, these are improper integrals, so there's some justification to be done, but it actually does work here, that we can combine these two integrals together into a single double integral, and that turns out to work. And if we do that, then we're going to multiply together our two functions. The theorem that we'd seen previously had us factor. The opposite of factoring is to multiply together. And so if we do that, we can write those as the sum of the exponents. And if we factor out the minus 1/2, we've got x squared plus y squared, and dx, dy, dx, it doesn't matter here. And this looks like it is perfectly set up to be switched to polar coordinates. There's our r squared sitting right in the exponent. The question is, what do we do with the bounds? So the bounds we have to remember are filling up the entire plane, right? That's what that is. We're going from minus infinity to infinity in x and minus infinity to infinity in y. So that's filling up the entire plane of R2. And how do we do that with polar coordinates? Well, we don't need the angle to go to infinity. All possible angles around the circle are taken between 0 and 2 pi. Now, for each one of those angles, we do want our radius doesn't have to go from minus infinity to infinity, but to go from 0 to infinity. And as that swoops around for every single value of r, you're going to end up by filling out the plane like that. And so we need 0 is less than or equal to r is less than or equal to infinity. So our double integral becomes the integral from 0 to 2 pi, the integral from 0 to infinity of e to the, and we'll switch here to 1/2 r squared and r dr d theta. Now this r is a godsend because it is the missing derivative of the exponent, and that is exactly what was sort of standing in our way in the single integral, is that we had no derivative outside to do a substitution. And so we can go ahead and make that substitution. The first thing I'm going to do is factor back. We see, and again, this is an improper integral, so some justification is required, but it does work. I can factor out the first integral, so 0 to 2 pi of d theta, and the second integral I'm going to rewrite as an improper integral, so times the limit as t goes to infinity of the integral from 0 to t of e to the minus 1/2 r squared r dr d theta. Now that first integral is a piece of cake, so we're getting theta from 0 to 2 pi. The second integral, well, let's do that substitution. So we're going to let u be 1/2 r squared, which means that du is going to be r dr, super convenient. Oh, I just saw a mistake. There's not supposed to be a d theta up there. And if that's the case, when r is 0, we get 0. When r is t, we get 1/2 t squared e to the minus u du. So this second one is giving us, or first one is giving us 2 pi minus 0 times, and now we have the limits as t goes to infinity of antiderivative minus e to the minus u from 0 to 1/2 t squared 2 pi, which is looking good for our final answer of root 2 pi. We need to do the fundamental theorem here, so minus e to the minus 1/2 t squared minus plus e to the 0. This is 2 pi times, well, the limit as t goes to infinity, we're going to get minus infinity up here. That's going to go to 0. Plus e to the 0 is 1. So our integral I, getting ahead of myself here, our integral I is, or I squared is 2 pi. Therefore, I, which was the integral from minus infinity to infinity of e to the minus 1/2 x squared dx, is root 2 pi as required.